Hi, my name is Kuriwara and today I will be presenting on methionine, an essential sulfur-containing amino acid. I'll be going over all the different types of characteristics this molecule has and the importance of these chemical features. Some general information about methionine is that it's one of the amino acids used to build proteins, making it an essential amino acid. Its molecular formula is C5H11NO2S, and its molecular weight is 149.2 grams per mole. This molecule melts at 280 to 284 degrees Celsius. However, it does not really have a boiling point as it starts decomposing at 181 degrees Celsius. Additionally, it is highly soluble in water and has low solubility with most organic solvents. When we look at the Lewis structure of methionine, every atom satisfies the octet rule with no formal charges, meaning that it's a neutral state. As one can see, I have labeled each atom with its hybridization and classification based on what's attached to each atom. Based on the classifications, the purple carbon is considered just an sp3 methyl group with no classification since it is not directly attached to any carbons. Next, the sulfur is sp3 hybridized with a secondary classification because it is attached to two carbons. The red carbons are all sp3 hybridized, but the carbon attached to the sulfur is a primary carbon, while the other two are secondary carbons due to their attachment to two carbons. The primary nitrogen atom is directly attached to a carbon and is sp3 hybridized. Additionally, the blue carbon is a primary carbon with sp2 hybridization due to its double bond to the oxygen, similar to the green primary oxygen, which also has an sp2 hybridization. Lastly, the primary oxygen in yellow is sp3 hybridized. Additionally, there are strong intermolecular forces such as hydrogen bonding in the NH and OH groups. The dipole-dipole interactions are the polar groups of C double bonded to the O and the C double bonded to the N. Lastly, the weak London dispersion forces come from the nonpolar thiether sulfide and the CH bonds. As stated, these hybridizations determine the bond angle and molecular shape of each atom. The red sp3 carbons have a bond angle of 109.5 degrees with a tetrahedral shape. It is important to note that when the sp3 and sp2 atoms have lone pairs, both the bond angle and the molecular shape may change. Therefore, the pink sp3 sulfur with two lone pairs has a bond angle of 105 degrees with a bent shape. The orange sp3 nitrogen with one lone pair has an angle of 107 degrees with a trigonal planar shape. Next, the blue sp2 carbon has a bond angle of 120 degrees and is trigonal planar, while the green sp2 oxygen with two lone pairs has a bond angle of 180 degrees with a linear shape. Lastly, the yellow sp3 oxygen atom has two lone pairs resulting in a 105-degree angle and bent shape. Methionine has three major functional groups that contribute to its reactivity and physical properties. The first one being the thiether sulfide, then the amine group, and the carboxylic acid. In terms of its resonance, methionine has two resonance structures involving the carboxylic group as shown in the slide. The bond between the carbon and the oxygen shifts to the oxygen, and the oxygen's lone pair shifts to the bond between the carbon and the oxygen. This results in one oxygen having a negative charge while the other has a positive charge. The resonance hybrid shows how there is partial negative charge and a partial positive charge between the two oxygens. Therefore, the delocalization of charges is spread across multiple atoms, explaining why both groups are the same length. Based on the acidity and pKa values of the molecule, there are two pKa values. The carboxylic acid has a pKa of approximately 2.28, while the NH2 group has a pKa near 9.21. However, the thioether sulfide group lacks a pKa because it lacks an acidic hydrogen to lose in an acid-base reaction. The full IUPAC name of methionine with its stereochemical configuration is 2S 2-amino 4-methyl thiobutanic acid. The 2s indicates the configuration the alpha carbon has, which leads us to the chirality of this molecule. Methionine has only one chiral center, where the alpha carbon is attached to four different groups. Using the Conn-Ingle pre-log priority rules, the amine with the highest priority is starting with 1, followed by the carboxylic group, then the left-hand side chain, and then the hydrogen has the lowest priority. This arrangement gives an S configuration since it goes counterclockwise with no need to solve conformations because the lowest priority group is at the back and the highest is at the front. Additionally, methionine has two stereoisomers, an S enantiomer and an R enantiomer. The enantiomer of the original molecule places the amine group towards the back and the hydrogen on the wedge towards the front. This causes the S configuration to adopt an R configuration, resulting in an enantiomer. Since methionine is an amino acid, there has to be Fischer projection. The most oxidized carbon is at the top. The NH2 group is to the left, and the hydrogen is to the right. With the specific placement of the NH2 and hydrogen, the chiral center switches from R to S, resulting in the structure of the methionine. Specifically, it swaps from R to S because the hydrogen, the lowest priority atom, is on a wedge. In terms of the nucleophilic and electrophilic sites, methionine contains both sites. The nucleophilic atoms are the sulfur, nitrogen in the amine group, and both oxygens in the carboxylic acid group. What makes them nucleophilic is the electron richness, which makes them ready to bind to other molecules and donate electrons. On the other hand, the electrophiles are the carbon center of the carboxylic acid group and the hydrogens attached to the oxygen and the nitrogen. These atoms are slightly positive, which can be pulled off by a base, allowing them to accept any electrons. The I spectrum The IR spectrum depicts different peaks in stretching expected for methionine. The NH stretch is observed around 3,350 to 3,500, and the OH stretch is observed around 2,200 to 3,600, which are the broadest and highest in frequency and energy peaks. The C double bonded to the O has an approximate value of 1750 in the carboxylic acid. Lastly, the CS stretch has the lowest frequency of approximately 650 to 750. In calculating the degree of saturation, the equation helps determine how many double bonds or rings are in the molecule using the molecular formula of methionine. The molecular formula of C5H11NO2S helped plug in all the numbers into the equation. The equation starts with 2 times the 5 carbons plus 2 plus 1 nitrogen minus 11 hydrogens and then minus 0 over 2. There are no halides in this equation, which is why it is 2. Therefore, the oxygen and the sulfur atoms are not included in this formula. This results in a degree of saturation of 1, indicating that the unsaturation is present in the carbonyl double bond of the carboxylic acid group. This matches what we have seen before in the Lewis structure of methionine. Since the molecule contains no alkenes, which cannot undergo hydrogenation, an alternative method is available. The method is called dehydrogenation of alkanes, in which instead of adding hydrogens across the bond, it removes two hydrogens from the alkane, creating an alkene. Hypothetically, when you heat an alkene in the presence of heat and a catalyst, two hydrogen bonds are removed and a new double bond forms between the sulfur and the alpha carbon. Therefore, since that is the only place that hydrogens could be removed, methionine would undergo dehydrogenation. However, the sulfur atom stabilizes the molecule and prevents an unfavorable CH removal. This reaction has an unfavorable enthalpy change, but with a favorable entropy change. In conclusion, methionine is an essential amino acid that the body cannot produce and must obtain from food. It is found in high protein foods like eggs, chicken, and fish. Biologically, it initiates protein synthesis, it converts to SAM, supporting neurotransmitter formations and regulation of hormone levels. Additionally, this supports liver health by aiding in the breakdown of fats, regulating the metabolism and growth pathways. Chemically, this compound is added to animal feed to support animal growth and is used as a nutritional supplement for humans. Methionine is also used in pharmaceutical formulations that involve detox or liver support. Experts in biochemistry describe methionine as a critical regulator of metabolism, controlling the cell's methylation, a nutritional requirement for the body since it cannot be made in the body and must come from food, and is an essential protein for construction. As mentioned, some current applications of methionine include proper nutrition for proper growth, liver support, and supplement manufacturing. However, some future applications can be cancer research due to some tumors depending heavily on methionine, genetic control of methylation through SAM, and biotechnology. Biotechnology can be used to produce more methionine more efficiently in the global food supply. These are the references, and thank you for your time. I hope this presentation helped you understand the structure, chemistry, and the importance of methionine.